Okay. Okay, guys. So we're gonna. I'm gonna try to finish everything today. So it might be kind of long lecture here, but I'm gonna cover the rest of that one question we started. All those results. Those are pretty fundamental. The questions that follow number 12 are basically just like, hey, look at those formulas and examine the relationships between things like, the radius of the orbit and the velocity. So for example, we leave off yesterday, wasn't it? Part A, the result was that V is the square root of GM over R.
Yep.
I think that's wrong.
That's right.
So what that tells you is if you say you somehow moved your moon twice as far away, so we're double the distance away from the center of orbit, what happens to the velocity?
It would decrease by root.
Yeah, it'd be smaller by a factor of root 2. And yesterday, so Winslow brought up a good point yesterday. It was like just after class, which is basically this. Like suppose, this could be Earth, for example. And suppose you put a satellite. Okay, in orbit around the Earth. What you would do is you'd say, okay, what's the distance away from Earth that you want it to be? Do whatever you wanted. Then you'd say, well, we know the mass of Earth, so mass is known. The radius you choose, the one you wanted, we know what g is, and so then you'd calculate the velocity that was necessary to maintain that orbit stably. And so then Winslow was like, what if you went, so suppose you're a little bit faster than that. Suppose you accidentally sent it a little bit too fast, what would happen? What shape do you think it would be?
Spiral.
Yeah. It would gradually, it's too fast, it would spiral out. And the reverse is true. If it was too slow, it would decay inward and then crash. What you find a lot of times in practice is like, there's not much air resistance out there, depending on how low you are. But sometimes you might say, oh, this thing it needs a little bit of a speed boost. So you can actually go and adjust, adjust the speed so that you don't spiral in and decay.
Does that have that to do with the International Space Station? Something like that. I heard that.
Yeah, because it's always going to slowly get closer to Earth. Like I heard it's like 2035 is the year they think they have to either decommission it or move it somewhere.
Yeah, I didn't know about that, but that sounds, it makes sense.
Yeah, because the gravity's going to slowly pull it in over time.
Yeah, well, it's more like, if you have the right velocity, then gravity just is going to provide that necessary centripetal force. It's just that if there's any air resistance, which, depending on how high you go, you get into like what they call the thermosphere, and there's not many air molecules out there, but there's enough that over years and years it might provide just enough air resistance to like very, 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 very slowly slow something down. The scarier thing is, have you ever heard about how like if something were to like blow up there, or just if two satellites were to crash into each other, it would cause this massive chain reaction that would like wipe out all global communications. Because you have all these satellites up there. There's a ton of satellites up there. And what happens, they're going really fast. And so if two crash into each other, they would shatter into a million pieces. And then now those pieces all of them are like little bullets. They're actually traveling faster than bullets, but they would just be zipping around. And there's a radio lab about it. There's like a small committee of people whose job is to kind of like monitor it and try to see like, oh, is anything up there going to crash? It's like, I think they're talking to the guy. They're like, yeah, our staff's like 5 people. We're doing our best.
What can they do if they just
not much.
just sit there and watch it happen? I guess.
Yeah.
That'd be kind of cool.
There was another similar one about the group of people trying to look out for like a life-destroying meteor.
Oh yeah.
They just kind of look around there, and they were just kind of like, what percentage of the sky can you kind of like examine? They're like, it's something like 0.001%. Like, we're looking over there today. Oh, nope, nothing dangerous yet. So, and then what we'll talk about pretty soon here is like things like meteors and comets and comet's a better example. Here's the sun. The comets follow these massively eccentric elliptical orbits, and you can probably guess, maybe you can guess, maybe not, maybe it's not obvious, but when the comet is going pretty slow out here, and then as he moves in closer, he speeds up quite a bit. And we'll talk about why that is, based on things like angular momentum and energy. So anyway, let's finish up 12. So we got that big result there. So what follows from that is, what's the angular velocity? Keeping in mind, there's a really fundamental mathematical relationship between these two, right?
Mhm.
V equals omega r. That's not particular to orbits or anything. That's just a thing that's true. So therefore, my omega would be this divided by r. Now think about what's going to happen. Maybe it's nicer to write it like this. 1 over r times the v. But can that, what can you do with that? Beauty of maths. That's kind of like the square root of r squared, right?
Yeah.
So what's this going to be? There you go. So I mean, you may have wondered. We got this question before, and learning like math basics of. Do you ever get like a cubic relationship in nature, or even the square root of a cube, or in this case, it's the square root of the reciprocal of a cube? And yeah, so it turns out that the relationship between the angular velocity of a planet, well, assuming it's a planet in a circular orbit, the relationship between its distance from the sun and its angular velocity is a inverse square root of a cube. Kind of weird. Period. Hey, period. Got some relationships floating around here. We know that, for example, I don't know how you conceptualize this necessarily, but we know that omega is 2 pi times the frequency, and the frequency is the reciprocal of the period. There's other ways to get to this, but I mean, so you could say this is true. Some people, physics students and such, just memorize this result sometimes. I don't know. Does that make sense?
Yeah.
Or maybe I'll think of it as, maybe it makes more sense to just think of it as 2 pi times the reciprocal of the omega. You know, why does that make life easier? Well, I can just go that make sense?
Yeah.
Here's a math question. If you double the radius, if you double your distance from, say you're a planet, you double your distance from the sun, how does that affect the period?
It increases in pi.
Good. Good flex too, not saying √8. That's good. But it would multiply by the square root of 8, which is 2√2. So it's almost 3. It would almost triple it, not quite. Okay, so D, it's all making sense. I know this question it's a little repetitive. You're just like, okay, we're basically just manipulating this equation over and over. Yeah, that's what we're doing. What's a formula for the radius in terms of the other stuff, though? Well, specifically, what's the formula for the radius in terms of G, M, and T? So which formula am I rearranging? This one. So let's do this. How many steps do you need to show? I don't know. Step 1 would be divide both sides by 2 pi. right? And then square both sides. Can I square both sides and then multiply by GM? That'll be okay. And then you got to cube root it. So talk about a weird, talk about a strange formula, right? Does that all make sense?
Mhm.
So, now of course this would answer the question of, well, let's say I'm trying to launch a satellite. I know the period I want it to have. So suppose I want it to orbit the Earth, I don't know, once every 3 days. Okay, great. Then your period is, what is that, 72 hours? However many seconds that is. And then you'd be able to calculate how far you want the satellite from the center of the Earth to achieve it. Okay.
Isn't that cool?
Huh?
Isn't that cool?
It's neato burrito, right? So then E, I don't know, I'm going right to left for the mangas. E's a good one because it's like, well, I got a star in the middle with some mass M, and we've got some information about, say, one of the planets. So this planet could be Earth, for example. We know Earth's period, right? Who knows the answer to that?
That,
365 days.
Yes, exactly. You just turn that into seconds, and that's the Earth's period of orbit. So what's the formula for the mass in terms of G, R, and the period? Which formula are we rearranging? I guess we could go, this one seems like a good place to start.
Mhm.
Period, R, and G and M. So same story. Starting from here, you would divide both sides by 2 pi. And then square both sides. We're all okay with that, right? And then I could send M, the thing I'm solving for, over here. Or I could flip both sides, doesn't really matter. We can flip both sides or do this. I kind of like this. Send M over here. And then we're one step away, right? Because from here, you would just multiply both sides by the reciprocal of this, and you'd have, these aren't like super beautiful formulas. They're not the simplest relationships. But what that tells you is stuff like, suppose our year was longer. What would that tell you about how massive the sun was? If it took more time for us to travel around the sun, say it took 600 days. So increasing this would mean, the sun was less massive, which I hope that makes some intuitive sense.
Yeah.
If the sun was super massive, we would zip around the sun really fast, right? So a smaller period would represent a bigger mass of the sun, okay? Then of course the answer to F is, which value did not play a role in any of these answers? The planet's mass. Okay? So for us to infer the mass of our sun, we don't even have to know the mass of our own planet. Figure that out. Although how could we infer the mass of our planet? There's a famous object,
Mr. Moon.
Mr. Moon, yeah. The sun is to the Earth as the Earth is to the moon. So you could say, well, this moon, how long does it take, what's the moon's period? A month, right? Or roughly a month, right?
I'll just say
What? It takes about a month to go from full moon back to full moon, right? So
Is the ratio from the Earth to the Sun the same as the Earth to the Moon?
in the ratio of masses,
Because like, aren't they? Well, like, never mind.
well, there's a size ratio that's really weird. You ever seen it? You guys saw that solar eclipse.
Yeah.
We had a really good view of one. Weren't we like, our town was like very close to the actual totality path, wasn't it? I saw it and I was like, that looks almost like a perfect eclipse. Anyway, when was that? Like 5 years ago? 4 years ago?
Yeah,
That was pretty awesome. So, oh yeah. So okay. So the sun. So like, here's the sun, and then here's the Earth. I mean, so you can't draw it to scale because at this scale, the Earth is like a speck. But I'm gonna mess it up here. Here's the Earth, and then what you have is from a certain point. Like, let's say you live here. You draw this cone, and the moon like fits right in there perfectly. That's why. Okay, say the moon was way bigger, right? If the moon was way bigger, then an eclipse would be, here you'd see the sun in the sky. Here's Mr. Teletubby, right? And the moon would do this. The moon would come over the sun and just totally like, you'd be able to see that eclipse from like, you guys have seen the map of like the path of totality.
Mhm.
That path of totality would be huge. It would like cover the whole state of Montana, for example, if we happen to be the path. But the actual path of totality is this little skinny strip where like for us, I think you had to drive south to like,
It's like Oregon.
yeah, if you drove like 5 hours, I think you could have gotten in the actual totality path. But anyway, so the moon just so happens to be like almost the exact same size as the sun in the sky, which is just a weird coincidence, I think. Anyway, so then in the eclipse, the sun, the moon just barely covers the sun. You get a really cool effect. So that's kind of neat.
Because they're actually the same size in the dome.
True. Yes. Yes.
That's why.
In the flat Earth model, the sun and the moon are just the same size.
They're just projected on the snow globe. Right?
Yeah.
Projection on the dome.
How could you be like an ancient astrologer or astrology person? Astronomer. Yeah. They're different. The other one's like space racism. Yeah, how could you look up in the sky and go, I know the sun and the moon are totally different size. You look in the sky, they're the same.
That's why it took. I mean, when was Galileo? Like the year? Wasn't he in the year like? I'm gonna sound like an idiot. Wasn't it like 1400s or something?
Sounds right to me.
I mix up my history really bad, so don't cyberbully me. Oh, at 1500s. So that's like really recent. You know what's crazy is I don't know, you guys probably don't remember this. How many of you guys like in elementary school heard something along the lines of like, oh, Christopher Columbus, some people thought he was gonna fall off the edge of the earth, but when he sailed around, he showed that it was round. That's like completely idiotic. They knew in like 2000 BC that the earth was round. Like Aristophanes proved it. Not only did he prove it, he actually calculated the circumference of the earth like pretty accurately.
Didn't he have a guy walk like 100 miles or something and measure every single step, and they were off by only like 30 miles or something?
I'm sorry, I was way off with the date. It's 200 BC. Sorry, I was off by a factor 10. 200 BC, my bad.
There we go.
But the Egyptians had some pretty lit astronomy. But sorry, the Aristophanes, or Eratosthenes, I guess is how you say it. But he basically what he did was, sorry, I gotta get back to on topic here, but it is interesting. He was like, he noticed, so that Zach, you have the basic idea, which is like the sun, all the sun's rays are coming down parallel effectively because the sun's so far away and so big, they're effectively parallel rays. And so like they dug a hole and showed, like they kind of waited for like, okay, well, let's dig a hole until the sun goes perfectly in there. And then also do the same thing like when the earth is rotated. And they picked another spot sufficiently far away. I think it was Alexandria and like the other spot was, I can't remember. One's Alexandria, The other one's some other spot, Detroit or something. Anyway, and they were like, they knew how long this took, right? And then they measured, they actually, like, I think they walked it off or something. They like, oh, this is so many miles. And then they did some geometry and showed that, because first of all, if the earth was flat, then both cities would agree, oh yeah, right at 2:27 p.m., the sun is directly overhead, but they didn't, obviously. So then they measured, so they calculated this angle, and then it's pretty, so here's R, and they knew this was L, and they know that L equals R theta, so the calculation is relatively simple to figure out what's the R value.
That is crazy to think that yeah.
Yeah, it's pretty ingenious, but I just find it funny because it's like even 200 BC, every educated person knew that the earth was round. But even before, I mean, he literally calculated it. But even before him, they knew it was round, just from like sailing around, like doing some sailing and stuff. And also literally just get in a boat and look. But anyway, but as far as like calculating the circumference and stuff like that, it was all pretty well established.
I was watching a privilege channel was on, but they took like a bunch of flat earthers out in California.
Uh-huh.
They got on like the biggest lake there or whatever, and they had the boat with like a big, I mean, it's basically a sign, effectively. They went out and, you know, obviously you can start to see like the curvature.
Mhm.
They're like, okay, like obviously the earth is round, like you can see that it's going down or whatever. All the guys were like, no, the waves are just getting bigger. It was just funny to hear, like, listen to them try to refute it.
I know. And anyway, with the heliocentric thing is there's a lot of interesting history behind, you know, the history of science is very fascinating. I just Googled, I try to remember the name. Aristarchus of Samos, around the same rough time, 300 BC, had a pretty like solid heliocentric theory that the earth revolved around the sun. But it wasn't really until, it wasn't like, I guess, proven mathematically until much later. But same thing with atoms. You guys ever heard of the atomists? This is way back in ancient Greece. They were the first people to be like, hey, what if everything was made of like these little tiny fundamental bits? Anyway, so, but it wasn't until thousands of years later that they actually were able to like experimentally and mathematically show that these things have to exist.
Even like the Egyptian.
Anyway, real quick. Okay, so I want to go over. So the questions that follow number 12 are all the same kind of thing. I hope you'll have work time next week during the AP week to just knock them out. But I did want to go over one really interesting one super quick, and then I need to go over energy. So that won't take too long. But so look at 24. Take a second and just read that. And some of you guys maybe have heard of that. Some of you guys maybe have not heard of that. But, huh?
What do they call it?
Geostationary.
Yeah.
So, this is the Earth.
Oh, isn't this like, they wanted to do this, cell service everywhere by launching a whole bunch of satellites.
Yeah, the Starlink. Yeah.
So-
yeah, they're doing like Wi-Fi.
Yeah, the first thing is just the fact that this is, I mean, how many of you guys knew that this was possible? Like, knew about these? Okay, some. Yeah, I remember, I mean, I learned about this fairly later in life and being like, wait, they can do that? And then I like did the math and I was like, oh, that's amazing. I'd never heard that mentioned before, but it was kind of amazing. I'd always assumed that satellites had to go way faster than the Earth's orbit, but. Okay, so anyway, so the Earth. Now here's the thing, the question's asking, how high does a satellite have to be above the Earth's surface, right, for this to work? So I actually have to account, this is the Earth's radius. Here, let's call this, I don't know, the height of the satellite above the Earth. Does that make sense?
Yeah.
What's the true distance between the satellite and the Earth? R plus 8. Now when I say true, I mean the distance between their center of masses is what matters in the math, in calculation. So what you do is you'd say, okay, well, it's asking for the velocity, right? So you would need to talk about, well, I don't know if I have time to fit. I need to get some more stuff done, but anyway, let's at least set it up, and I think I'll save it for you guys to see if you can figure it out, because you have to go same argument as before. We'd say, okay, well, the force is equal to the mass times v squared over r, right? And so the force would be your gravitational force. So G, let's do a little m for the satellite, big M for Earth's mass. This is the h plus r squared. Does that make sense from the Newton's gravity formula? And for centripetal force, it's little m times v squared over. That makes sense. I mean, maybe I should have written it like this. But I'm just showing you, I'm setting it up exactly the same way we did before. Right? Except instead of, why did I put r plus h after writing h plus r? I don't know, guys. I'm sorry.
I forgive you.
Yeah, thanks, Griffin. Thanks for the 100 bits. You're gonna have to figure out basically what's gonna be the combination that works. And there's a trick here. You might also want to incorporate your other formula, because what's a critical piece of information for this question? What value do we know? The period. Because if this satellite's going to stay right over my head the whole time, what has to be the period of the orbit? No. How long does it take for the Earth to do one rotation? 24 hours. We're working in SI units, though, so you can turn that into seconds. So 24 hours in a day, there's 60 minutes in an hour, and there's 60 seconds in each minute. So I'm going to save the rest for you guys. So you're going to use a combination of the stuff we just did, those formulas that relate velocity to distance and stuff. You might also throw in the period formula, if that helps, or you might just do a substitution right here, replacing the v, right? You can calculate the v since you know the period and the distance. Or sorry, you can make a relationship, that's what I meant to say. You can write a relationship. Anyway, we'll see if you guys can figure that out. And I gave you the Earth, the mass of the Earth and the radius of the Earth. So you can plug in those values. Okay? You feel okay about that? All right, last thing to cover is gravitational potential energy. And you might be thinking, wait a second. Didn't we just do that for a really long time? Now, this is something that almost every student of physics forgets, which is understandable because we pretty quickly derived that. What's that formula for gravitational potential energy that we've been using all year? Not all year. MGH, right? Very quick overview of that. Well, where did that come from? Well, what we did was we took a block of mass m and we lifted it a distance h and made an argument that, well, since the change in energy is equal to the work, and the work is force times distance, and the force is mg, and the distance I pushed it is h, then therefore the change in energy must be equal to mgh. That was the argument we made when we derived it. But there's a little problem with that if you're dealing with a long distance. So let's say here's the Earth, and you didn't just lift it a couple meters or a couple hundred meters. What if you wanted to lift the block several thousand meters? There's a problem, which is, well, we just showed that the force required to lift the block actually decreases as you move away from Earth, right? So this is true for small, or let's say it's close enough for small distances, right? But if it's a long distance, then the force out here is way, way, way less than it is here. Does that make sense?
Yeah.
So for you calculus people, what you actually have to do is you have to integrate a force function over a certain distance to calculate the work. That's the full story, actually. Now, of course, if you can say that, oh, the force is roughly constant, then you can just, you end up with this result. But I don't know. Am I confusing you guys? Or just makes sense? Obviously, if you didn't take calculus, that makes no sense. So ignore that. But the idea that at a small scale, the block weighs the same amount here as it does here, but on a longer scale, the block weighs less here than it does here. So therefore, it's actually a bit more complicated than MGH. So here's the formula. We have to use calculus to derive it, so I'm not going to cover that. The gravitational potential energy is negative G times M, let's call it M1 times M2 over R. Not R squared, just R. You guys okay with that?
I could be.
And so what that means is this, okay, so if this is, let's redraw it. If this is M1 and this is M2 and they're separated by a distance R, then this system contains gravitational potential energy. Now, why is it potential energy? Well, what's going to happen if let's say I'm Galactus. You guys know who Galactus is?
Yeah.
And I'm holding these out in space and I let them go.
He's huge.
Yeah, he's a huge guy.
And the Silver Surfer is a little dude.
Yeah.
Like Jacob?
You what?
Yeah, I think.
And like fight.
Yeah, you got it.
Probably you could.
Yeah.
Not me. I bet too much soy milk. So if you let these go, what are they going to do? They're going to crash into each other eventually, right? They're going to be attracted to each other. They're going to speed up because as they get closer, the force increases. There'd actually be a ton of energy. They're going to slam together. So, where'd the energy come from? Well, it was stored in the potential energy of the system. Okay. So for you calculus fans out there, you might be thinking, actually that kind of makes sense because the integral of a 1 over x squared would be a negative 1 over x, wouldn't it? And that's our force function is like a 1 over r squared, and our energy function is a negative 1 over r. Right? So, just for funsies. So, we could calculate 25. Let's do a quick calculation.
Let's do it.
And I'll probably have to, I guess I'm gonna have to save escape velocity and stuff for tomorrow. And then, okay, at least we'll be able to cover it all without rushing too much by the end of the week. So calculation, I've got a 2,000 pound rock. It doesn't say pounds, is it? Okay, kilogram, sorry. 2,000 kilogram rock. So that's mass, that's one of the masses. It's initially at rest and it's 400,000 kilometers, which means it's 400,000 meters, right? Make sense? Also known as 4 times 10 to the, 368 meters. So that's our R value. And it's close to a planet. Does it say it's that far from, the planet's just over here. And it's 3 times 10 to the 25th. The question is, how fast is it moving when it reaches, I don't know why did it shrink? I don't know, guys. Here, we're consistent. It's still changed size. Okay, there you go. The question is, how fast would it be moving when it is only 100,000? Meters. So when it's a quarter of the distance away. Does the setup make sense? So all you would do is you'd say, well, start with the energy. So we'd say the total energy of the system before is equal to the total energy of the system later. Initial energy equals final energy, conservation of energy. And so the initial energy is negative G times the product of the masses. Huh?
The 4 times 10 to the 8th is the radius.
Just testing you, Kate, obviously. just testing. Thank you, Kate. What would I do without you? You lost in the digital dust. And obviously I didn't leave enough room because I'm dumb. But over here, you'd have a sum of two terms. You'd have, well, I try to squeeze it in here, G times 2,000 times, I hope this is legible. But over here, the new radius is 100,000. So that would just be 1 times 10 to the 8th, right? I'd say 100 million meters. Does that make sense? And then plus, what other form of energy exists now? Kinetic. Kinetic. It's moving now, right? So we're solving for V. So you go plus 1/2 m v squared. Does that make sense? So part of what makes this interesting, this didn't annoy anyone?
Negative.
Yeah.
We have 2 negatives, so they'll cancel out.
Well, here's the thing. This is the thing that it should annoy you. Here. What happens to go back to basics. What happens to the potential energy when this thing goes lower?
It
Decreases, right? So hopefully this doesn't blow up that entire concept. That would be extremely annoying. If, all of a sudden, when the thing, Colin, can you put that away? When the mass gets closer to the other mass, right? The gravitational potential energy should decrease. Now, is that what we see here? If R gets smaller, right? Ignore the negative for a second. If R gets smaller, what happens to this overall number?
It gets larger.
It gets larger, but it's a negative number. So a larger negative number is actually a lesser value. So as you get closer, the potential energy is decreasing. Does that make sense?
Yeah.
But if I can graph this, by the way, I can do here's what the energy versus distance graph would look like. And that's just, it's like a 1/x function, but negative. And so you can see that as the R gets smaller, as you decrease your R value, you're actually lowering the potential energy, which would thus increase the kinetic energy. So what I guess I'm trying to show you is everything still fits together perfectly. It's all like, you don't have to you don't have to throw away your knowledge of the whole MGH thing. Just understand that the MGH thing is just a local approximation for small distances. Anyway, so Mr. Quackmolator. So if I go, do I still have G stored? I do. That's nice. So if I go G, so negative G times 2,000 times 3 times 10 to the 25th. Okay. Divide that by 4 times 10 to the 8th. I'm sorry, I know the numbers get really big, it's a little annoying. So I've got this number, and I'm basically gonna this is a negative number, so I'm gonna add that on to that side, or I could subtract the negative value, but I'm gonna go plus, my calculator, I'm going plus G times 2,000. Hopefully a few of you guys will do this with me so that we can check. My odds of making a mistake here are considerable.
Your track record isn't great today, Mr.
I know. I'm getting a number very close to 3 times 10 to the 10 equals, what's left over here is my 1/2 mv squared. So I don't know. See if you agree with me there. So unless I made a mistake, that would be your final answer. Which is fast. It's a fast dude. And keep in mind, I mean, he hasn't even really started to speed up yet, if you think about it. I mean, what's happening to the force right now? As he gets closer, what happens to the force exerted on him?
Greater.
It gets bigger and bigger. So he's going to gain a ton of speed in the last bit there. Anyway, check my math there. That should be, I think it's correct as best as I could do it.